So we learned about demographic noise and how to incorporate demographic noise, right? In simple models, okay, using the idea of chemical Langevin equation. Okay, and what we also showed was that for the simple binary choice model, which can be interpreted in many different ways, right? It can be applied to the context of opinions, behaviors, and so on, and even simple movement choice. Okay, so we showed that it has the demographic noise. If you account for the demographic noise, the equation would look something like this: m dot is equal to minus 2sm, right, plus 1 over square root of n. I think it was 2 over square root of n, square root of 2s plus c over 2, 1 minus m square. It's times eta t, where it is a Gaussian white mass. Let me just make sure I got the equation right. There was no 2s, there is an s. Okay, this is what we had. Let us try to understand this equation a bit better. So consider the case when noise is 0, right? We ignore the noise. Ignore stochasticity. What will you find if you ignore stochasticity? You just have a simple equation, which is m dot is equal to minus 2sm, right? What would that mean? This is a simple exponential differential equation. So m of t is equal to m0 e power minus 2st. That's right. So if you ignore stochasticity, what this equation shows is that m, which is a parameter measuring consensus, actually decays exponentially from whatever the initial value of the consensus is. Okay. That means that if I ignore stochasticity, which is same as basically deterministic mean field approximation. Mean field deterministic approximation predicts that the order of the consensus in the system decays exponentially towards 0. Okay, that's what we will find. Deterministic approximation. However, we do have the stochastic term. So what does the stochastic term mean? Okay. Let us try to understand this. Okay, so as we know, we call this a multiplicative noise because the strength of the noise depends on the state system. Let us plot g of m as a function of m. Did anyone have a question, by the way? Okay, so what does this multiplicative noise do now? So let us plot g square, because there is a square root, right, as a function of m. What does this look like? So, as you know, m is x1 minus x2, where x1 is a proportion of individuals in state 1, x2 is a proportion of individuals in state 2. So m can only take values between -1 and +1. So in fact, we should have this from -1 to +1. Okay. Okay. So let us look at g square. So g square is equal to 4 over n, yes, plus c over 2, 1 minus m square. When m is equal to 0, this is basically 4 over n times s plus c over 2. Okay, so some constant, which is 4 over n times s plus c over 2. So now it's proportional to s plus c by 2 times 1 over n. Okay. When is this minimum? We know what, when is this minimum? When m squared is maximum, and m squared is maximum when m is equal to 1, right? Or minus 1. So it actually reaches a minimum value when you are at this extreme. Okay. And that means that and at that value of m, it will be basically 4s divided by n because this term goes to 0. So this will be okay. So and then this is a square terms as a parabolic equation. So let's expect this to look like this. Is everyone fine with this? Okay. So what you have is a multiplicative noise, which is maximum when n is equal to 0 and minimum when n is equal to minus 1 plus 1. Okay. And then if you look at the deterministic part alone, what is the equilibrium? Let's now plot that also. If I were to plot just the f, how would that look like? It's basically this. This is basically f is equal to minus 2. The slope of minus 2s. Okay, and then this is how it looks like. So if I analyze only the deterministic equilibrium, what will I get? This is the equilibrium and that's actually stable. However, what's happening in the deterministic equilibrium? The strength of stochasticity is actually highest. And then the strength of stochasticity is low when I am at far from the deterministic equilibrium. Does that ring a bell? Have we studied a model like this anywhere in the class so far? Have we studied a model like this so far? Does anyone remember?
We try to model home range.
Okay. That is a model of home range we studied, right? Do others remember? In fact, I had given a lab work, right? Isn't that right? Remember, we had studied a whole bunch of models for home range. We wrote x dot is equal to minus alpha x plus eta t as the simplest model of home range, right? And then we studied another model where we said, the farther they go, more deterministic they become. And therefore, we argued that the stochastic term must look like this, where this is the origin. Okay, and then I had asked you to write down your own function where the stochasticity is maximum when they're at home, but it's actually least when they're far away. And then you have done this. That's more. I hope partly some of you remember, and if you actually remember, I had also given this problem either in the midterm or the end term of the last year's exam, EC 201, where I had just given you the equation and I had asked you to numerically simulate and understand what's happening. Okay, so we have come across this model actually several times. At least the mathematical form we have come across several times. Of course, only now that we derived from first principles for a scenario where the mathematical form is explicitly like this. Of course, because we derived from first principles, we are actually able to make we are actually able to say very interesting things. So here, when we were writing these phenomenological models with some context, we would just write down parameters and functions in an ad hoc way, in an intuitive way. Here, the difference is that this form actually was a consequence of the derivation from first principles, which used in this case, chemical engineering equation. So now for the binary choice model, which I have introduced several times in the course, right? Would you have expected that the noise term will look like this? Or can you intuitively justify why is the noise term looking like this? Why is the noise term not an additive noise? Why is the noise term in an inverted parabola, an upward, like a cup instead of a dome shape? Can you intuitively justify why does the noise term look like this for a binary choice model?
Because when m is equal to 0, the population is most divided. So there is most like stochasticity is not dampened, and at either end, like -1 or +1, there's consensus, and so stochasticity has to be low.
Why is the stochasticity low in this consensus? You're right.
Sir, when there is consensus, we have one class of reactions which completely go away, right?
What is that?
Switching reactions go away, and one of the copy reactions also go away because either XA or XB becomes 0.
Okay, that's it.
Right.
So an intuitive way of thinking about that, maybe I just do it here only. So we have two reactions, like the spontaneous reaction, right? You may go right below. I don't want to clutter the space. Okay. So question is, how do we intuitively justify intuitive explanation? So both of you have given the answer. That's very nice. For g square of m for the binary choice model. Okay, remember that the binary choice model has these reactions, right? There's a spontaneous switch. Does the spontaneous switch depend on what the others are doing? If there's an individual is in state 1 or 2, okay, does the spontaneous switch depend on what others are doing?
But it does require individuals of state 1 or state 2.
That is right. Understand one subtle thing always in ecology. Density dependence is defined once an individual is given.
Sorry, I don't think I understand what that means.
I mean that once there is an individual of x1 or x2, does this reaction depend on the existence of others?
Right.
So the existence of others is defined only when the individual of one type is given anyway. Right? So okay.
Yeah.
Take it is given, it's conditional on the existence of one
Right.
other. If it is there, then does this reaction depend on the other type?
It doesn't.
It doesn't, right? So this doesn't depend on. That means, remember that both of them are probabilistic reactions. Okay. That means that this term, the spontaneous reaction term, is always present. It is true, is same, independent of m. Right? Of course, in the extreme limit of, let's say, s equal to 1, even then it's present. X2 is present, X2 will turn to 1. So it will generate that, some change because of this, right? So this reaction is independent of m. Okay. On the other hand, what about this reaction? It becomes 2x1 or 2x2, right? Okay. So let's consider one extreme where let's consider only one of the type of reaction. X1 plus x2 is 2x2. What does this really mean? If you were to think of this in a very general way, how does this actually happen? There is a whole population, right? Okay, there are lots of individuals. Some of them are 1, some of them are 2. Okay, and the way this reaction is implemented is that an individual, let's say, first you choose one individual, and then this individual chooses a partner, X2. Okay, you choose another individual, and then you copy the behavior of that individual. Okay, now imagine that everybody is one extreme where everyone is one. So if this is the focal individual now, F, okay, and if this person chooses a random, let's say the frequency of 2 is very, very low. Okay, if this person chooses a random individual, who is that more likely to be? It's going to be that of another one, right? So even if you were to rephrase this, this reaction as two individuals meet randomly and interaction happens where one of them copies the other, what is the most likely outcome of this reaction when everybody is one? Of this reaction when nearly all individuals are one. What is that? Okay, I think I understand the confusion. I think, because I have written this in a way which is x1 times x2, x1 plus x2, here it is given that x1 is interacting with x2. Okay, maybe I should, let us rewrite this equation in a better way. Okay, two random individuals interact. One of them copies the other. Okay, let us think of this reaction in this terms. Then what is the most likely outcome of such a reaction? By the way, first of all, you must convince yourself that this reaction is actually same as this statement I wrote here. Okay. So that's something, it will take some time to sort of map the two. Okay. And this is a density dependent reaction. Okay, unlike the previous one. So what's the most likely outcome of this? If everybody is one, n is in state one, two randomly chosen individuals, what would their state be? Most likely state of both of the individuals. They would both be in state one, right? And what's the outcome of, if you now force this reaction between those individuals, what will be the outcome? Nothing, right? Because if two individuals of same type interact, the outcome is actually same type anyway. Which is why when individuals, there's already a consensus, and very good, nearly complete consensus, the stochastic contribution of this term will be basically closer and closer to zero. And that's what causes this to go down. Okay. And that's what causes this, this behavior. So the copying, this reaction is happening at a rate C. Okay. And then, but the contribution it actually does is 1 minus m square, not m square itself, because the contribution happens only when they're unlike each other. If they're like each other, the outcome is actually nothing. So m dot will be 0 in a deterministic sense. And so will be it actually in a stochastic sense. Okay, so therefore, its effect is least, when m is actually equal to 1. Okay? So this explains why copying reaction actually has. So copying reaction doesn't contribute deterministic term because it is symmetric. X1 and X2 leads to X2, and X1 plus X2 can also lead to X1. That means that it is symmetric in both directions. Therefore, it has no contribution to the deterministic term, which is a mean term. But it does have a contribution to stochastic term. But the stochastic term contribution reduces when everybody is similar. When everybody is similar, copying interaction has no effect. Okay, so that's why it has lower effect even in the stochastic term. And that basically causes this parabolic, sort of inverted parabolic shape. Does that make sense? Okay, I hope, if not, please think about this a bit more. Okay. And then that's the intuitive explanation. And the another connection I spoke about was that of home range. Do you remember the results you got for the home range when you did a model like this? Okay, I don't know if you remember. It will be in some lab, and I think you must, if you have done that, if you remember that the strength of stochasticity determine the outcome of the likely stable state. And I also described a notion called noise induced state. Okay, so let me just revise those results in the context that we have done. I'll just state the results. I will just and I hope you can. Again, not sure if the 2 comes within the root or is it actually outside the root. I think it's outside the root. Huh? Okay, so what we find here is, how do you go about solving this equation mathematically? Okay, now this requires you to write down what we discussed previously, which is Foucault-Planck equation. So Foucault-Planck equation will basically determine how probability of the probability density function of the the variable m changes with time. Okay, so it determines how this changes with time. Okay, so it will be a partial differential equation. I don't intend to solve that here fully. For those of you who are interested in mathematical aspects, please do this. And the book chapter that I actually shared with you has all the calculations. Okay, and then if you saw, what you can then do is solve for the steady, what we call the stationary state, where the left hand side becomes 0. So steady stationary state Ps of m, where this probability density function doesn't change with time anymore. Okay, and what you find is that this depends on the strength of noise. What is the strength of noise in this model? Of course, it's the multiplicative noise strength. But if you think of a parameter, the strength of noise comes from this term. Let's call that sigma. Sigma is basically root of 4 over n. So what you find is something very interesting. Okay, let's say we are plotting P of Ps of n as a function of n. What you find is that when sigma is less than some threshold value, let's call it sigma c, small values of sigma. What does small value of sigma mean in terms of n? N is greater than nc. When the population size is large enough. Okay, what you find is along our intuition, which is that deterministic equilibrium is 0. What you will find is that the PDF basically shows a maximum at 0. Okay. On the other hand, when when sigma is large, this result actually changes dramatically. You find that the probability density function shows kind of a actually just changes the pattern entirely. It has maximum value close to 1. Okay, it will look like this. This is for sigma greater than sigma c, which means that for small size population sizes, for small group sizes, depending on the context you're thinking of, it actually shows the opposite pattern of what you expect by deterministic states. And what this PDF means is that the most likely state is the +1, meaning everybody is in state 1, or -1, which is everybody is in state 2, one of the two. And in fact, you may even find switches between the two if n is actually sufficiently small. Okay. And what you find is that at this sigma c, we sort of find sort of a, something like this, almost like a uniform distribution. In terms of n is equal to nc. Okay. So you find this kind of a very interesting feature where the state of the system, let us be more precise, let us say the most likely state of the system, most likely means mode, okay? Most likely state depends on strength of noise. Okay, and not just in a quantitative way, it's qualitative way, it's qualitatively different. Qualitative dependence on sigma, and such behavior is called noise-induced transitions. The transition as a function of sigma is called noise-induced transition, and the result you find because of this, that is a state that is most likely, that is far away from the deterministic state. Okay, and that is happening because exactly where the deterministic state exists, the strength of noise is maximum. Okay, therefore, when the strength of noise exceeds certain threshold, it can actually kick you out of deterministically stable state and make some other state actually stable. Okay. So this would be called noise-induced states, whereas the transition itself is called noise-induced transition. Okay. And and I think this specific model actually has been discovered and rediscovered in various contexts. If I'm right, there were some models in the context of ant colonies in 1990s, early 1990s or late 1980s, that did some, I think, numerical implementation of these models, and there were papers in the context of financial markets. Okay, now the two states actually become two stocks that people are buying. Okay, and when they're buying, they spontaneously switch between buying one stock, one type of market, one type of company, another type of company, but they also copy others' behaviors when they're doing so. So financial markets was another context again in 1990s that people studied. Okay, and in 2014 there was a paper in Physical Regulators that again sort of analytically derived the ant colony model. Okay, and it was published in physics journal. Okay, and that's where it was again sort of I think shown in a more formal way. Okay, and so this is this sort of model has had an interesting history, and I think so this is a literature I'm not particularly familiar with. There's literature called opinion dynamics, and my understanding is that this model sort of broadly falls into those class of models as well, except that in many cases, people often do not focus on the small or finite size effects. They often focus on n large. So therefore, they often miss out on this very interesting pattern that I drew in the blue color. Okay, so in a lot of the cases, people just miss out primarily because they actually don't focus on the small, the effects of stochasticity arriving when the system size is small. So in that sense, the Biancoloni paper does a very clean job of highlighting that small size effect very nicely. Okay. Okay. So now I had also asked you more. Okay. Any questions on this before I go forward? Any questions?
The second operating system be well mixed, right?
Say this again.
Well mixed system, right?
These are all well-made systems because this is a mean field approximation, right? But stochastic mean field, right? So basically, this model is stochastic mean field approximation. Any other question? Okay. So now in the class, in the last lab assignment, I have also asked you, okay, to sort of derive an equivalent equation for the ternary choice model. Okay, please do it. I think it will be an interesting exercise. Okay, it will take some effort and time to figure out, but I think it's an interesting exercise. Okay. Now let us ask the following question. If you're all done with this, let's ask the more general question. Let us ask this. This question can be asked in many different contexts. Let me state the general question, and then a more specific one. Let's say we have some measurement of macroscopic. This is given to us. Okay, let's say from data or from somewhere. Okay, as you do know, we are often interested in writing a mathematical model that explains or that understands tries to do something with this macroscopic property. But we can ask the following question. There is a model M1 that makes some prediction about, let's call this Q, okay, about Q. There's another model M2 and make some prediction about Q, and so on. We have a number of models, they all make some prediction about Q, right? So our eventual goal in mathematical modeling exercise is to find out which is the most appropriate model. Okay, this is often sort of the question people mean when they say, okay, you have one more model of this phenomenon of biology, but tell me which model, why should we believe in your model but not someone else's model? Okay, so the key way to understand the question is that there must be some measurable quantity we have in our mind, and then we then have a gallery of these models, or zoo of the models, all of which make predictions about Q, and then we pick the model that actually makes the best prediction about Q. Okay, that's the standard way science works, and we all know this. Okay, but here is the challenge. Let's take the context of collective motion, collective behavior, about which I gave a few examples, right? Collective motion in animal groups. Okay, I also showed you videos. I also did a couple of classes on two models. Here, people had observed collective behavior. They saw these fascinating patterns of birds, fish, and so on and so forth, moving in groups. And then they built a whole bunch of models. There was this Boyd's model by Reynolds, right? And there was a Vichek model, right? And then there was this cousin model, which was similar to Boyd's model, and so on. There were all these models. Now, if I ask you, of course, they all incorporate different degrees, different levels of realism in those models. But let's ask, were they actually focused on modeling in the sense of what I just described above? And then, of course, moving forward a bit, I told you that if you think of binary choice model, and let's say ternary choice model, okay. So there, individuals were choosing between two choices, right? Let's think of a simple scenario where, an experiment is done in an annular arena. I think I showed you this example of locust experiments where, individuals, could move either counterclockwise or clockwise, right? And then when everybody moved in counterclockwise, n became 1, right? And everybody moves in clockwise, and n became -1. Okay, now so one can also think of using this binary charge model, which had much simpler rules. Okay, also as models are correct. So I can actually increase this set of models forever. Here is my question: how do we know which model is the one that real world organics actually follow? How do we address this question? Any thoughts on this? Okay.
Can you
Yeah.
ask the question again?
Yeah, sure. Go ahead. Yeah. You have your own question, is that right?
No, like, can you like explain it again? I didn't know.
Yeah, I'm asking actually a fairly vague question. Okay. Yeah, we have now learned so many models, say of collective behavior, collective motion, this, and we can ask now, and then which of the model is the correct model? Which model is more realistic? How do I go about answering this question? I listed 5 models here that we have studied in this course. I think Boyd's I did not really explain, so I can sort of say fine, I haven't explained, maybe just leave this out. Okay. So I have explained 4 models which can be sort of mapped into collective behavior. Which model is more realistic? How do I go about answering this question?
Like if all of them like corresponds with the data, right? The one with the simplest explanation.
How do I know they correspond to data?
Okay.
They all make reasonable predictions. They all look reasonable.
Mhm.
You could differentiate them based on the assumptions. So
Okay, that's a very good point. Okay, let's stick to basics. Differentiate based on assumptions. Okay, very good. What else? Okay, if I were to go by this, so is this same as this, or those two different approaches to testing a model, to validate a model?
Q is the like output, like end like output of the model, right?
So this is Q is the output of the model about a macroscopic quantity.
Yeah. So like the assumptions would be like the building blocks.
Exactly, right. So they're actually complementary approaches. One way could be differential based on the assumptions. The other, the one that I wrote about is differential based on the predictions. Right? These are actually 2 different approaches by which you can actually test models. Okay. Okay, so that's actually very important. So I think we both covered important ground. So let's see, what do we know? So I said I'll give you some examples of empirical work in this context. So let us look at the differential based on assumption. So they all make different assumptions, right? So for example, if you remember, Vichek model assumes that the copy average direction of neighbors. Okay, it does, cousin model does something more. If you look at the assumption, it says it actually includes attraction. You basically move towards neighbors. It actually again implements the same rule, copy the average direction of neighbors. It actually includes this. It also includes repulsion. It assumes that the attraction zone is different from the orientation or the copying direction zone, which in turn is different from the repulsion zone. And clearly, this appears more realistic, but it has things like repulsion. It has things like attraction, alignment. So it almost obviously seems that this must be a more realistic model than this. So why should we even look at project model?
Maybe the assumptions may not be that realistic to get the output, like the predictions close to the one.
Project model? Okay. So that's where, if we just go by differential based on assumptions, the more complex models will always appear better and better. Okay. Just because they appear better doesn't mean they're actually more realistic. Okay, it's very important to understand. So in contrast, now if you look at binary choice model, ternary choice model, did these models have space at all? Was there an element of spatial structure?
No.
It did. Whereas these two models are spatially explicit. So therefore, clearly these two models are actually really inferior compared to these two models because there is no space here, at least the way I have defined. Okay, so if one way is to naively think about assumption, therefore is not necessarily a sufficient way of eliminating more realistic models. Just because there are more realistic components doesn't mean they're better representative of data. Therefore, one has to work a bit harder to sort of see which models have more accurate representation of assumptions. Okay, so what I will do is that maybe today I will try to show you a couple of papers that tries to talk about the assumptions of the model. Okay, that tries to test the assumptions of the model directly. Maybe in the next class I will try to look at papers that will actually follow the latter approach. Okay, so today I will stick to the first one, which looks at assumptions. Now, one key, there are, if you think about it, the key assumptions in these two models is that there is a local neighborhood, right? And then individuals copy the behavior of the local neighborhood. Okay, that's what these two models try to do. Let me just stop sharing this window now. Let me just show you a couple of these are representative papers. They're not the only papers, to be sure. Okay, this is a paper of schooling fish. It was published in 2011. Okay, so let me just, because I haven't made slides, I'll just zoom in a bit and also maybe highlight some key results. Okay, so here, they're actually really focusing on the, individual level interactions. Okay, which is the key local assumptions at the local level, determining individual level interactions that govern highly coordinated motion animal groups or cellular aggregates has been a long-standing challenge central to understanding mechanisms and evolution of collective behavior. Numerous models have been proposed, many of which display realistic-looking dynamics, but nonetheless rely on untested assumptions about how individuals integrate information to guide the movement. So the key point here is, there are many models. They all produce realistic-looking flocking patterns, but we don't know whether the underlying assumptions about the interactions are actually correct. Here we infer behavioral rules directly from experimental data. We begin with analyzing trajectories of golden shiners, a type of fish, one of the fish species, swimming in 2 fish and 3 fish shoals. They're really small sizes, by just 2 fish and 3 fish shoals to map the mean effective forces as a function of fish positions and velocities. Speeding and turning responses are dynamically modulated. So then they sort of infer what exactly fish do. They say that speeding and turning are dynamically modulated and clearly delineated. So speeding depends on some type of rules and turning depends on some type of rules, which are the kind of things that you don't often incorporate fully in the simple models. So speed regulation is a dominant component of how fish interact, and changes in speed are transmitted to those both behind and ahead. So here is a very interesting thing. If I go back to those two models, cousin model and check model, right? Did they actually have variable speed in them at all? Actually, if you go and read the papers, you will see that they assume that the agents always move at constant speed. Okay, and they were only assuming modeling, the interactions under the assumption of constant speed. Whereas the study here shows that the speeding up is actually a really important part of the way fish interact. And then they go on to say alignment emerges from attraction and repulsion. And in fact, alignment is not a direct interaction, is the argument of this. And fish tend to copy directional changes made by those ahead. We find no evidence for explicit matching of body orientation. Okay. So by comparing data from two fish and three fish shows, we challenge the standard assumption ubiquitous in physics-inspired models of collective behavior that individual motion results from averaging responses to each neighbor considered separately. Okay. They also argue that the three-body interaction is substantial and so on and so forth. Okay. So basically, this is a case, it's an experimental study that actually tries to really identify what are the interaction rules in a given system. Okay. And they do this by looking at patterns, the kind of nature of forces at the very local scales. Okay, I'm going to jump to the first figure, sort of try to see what exactly they are trying to do. Okay, because I think the first figure roughly has all the most of the important results. So basically, there are two fish. Okay, so let's say this is the focal fish, and they quantify the current velocity, and they also quantify what they call speeding force and the turning force. Speeding force is radially towards the current heading, whereas the turning force is perpendicular. And what you have is then a resultant force, which is a combination of velocity, the combination of speeding force and turning force. Okay, and then they also know where the neighboring fish is. What they basically do is how is the speed of this focal fish is changing with respect to the presence of the neighboring fish. That's what they basically do. Okay, so let's look at the figure B here. In figure B, what they do is here's the focal fish. They first map where is this other fish present. Is other fish always present in the front or is it in the back? And they find this interesting heat map. In this heat map, blue means a very low probability of occurrence. Red means very high probability of occurrence. What you see is that the other fish is found mostly in this region around the focal fish at some sort of almost like fixed distance. The large part of it is either in the front or in the back. So directly in the front, with of course in a hot spot at around 45 degrees, and again you find them again in the back with a slightly more presence in the left side than the right side. I don't know if the difference is really large. And by and large, a large part of the presence of fish is in this what they have written as 50% ring. Okay, so that is where the other fish is found. Okay, this is the location of the two related fish relative to one another. Now let's look at the speeding force. Again, the red basically you interpret red as a high amount of force. Blue actually has the again high, but the dark blue would mean an opposite force. Okay, so this is where the focal fish is. What you see is there is a positive force whenever the other fish is present in this region. So whenever the other fish is present in this region, this focal fish has a tendency to move towards them. Okay, so whenever the fish is present here, of course, it doesn't move towards the back, but actually moves again towards the front, right? Because it tries to move away from the fish behind. So therefore, the sign actually gets inverted here. So it doesn't mean the fish will actually go back, by the way. So basically what this shows is that there is a massive amount of speeding that occurs when there is a fish ahead of you to catch up with the fish you ahead, in front of you. On the other hand, this is a map of how the turning force acts. Turning force will be maximum when the fish is on the either to the right side, in fact, probably maximum when it's close to 90 degrees from the current heading of the fish, or minus 90 degrees. Okay, I will turn towards in this direction. If the other fish is present here, and likewise in this direction, the other fish is present here. Okay, so this sort of captures the entire sort of average force map of how the two fish are interacting with one another. Does that make sense? Any questions? Yes. Okay. So I'll just this is one very nice paper that sort of tries to map the local level interactions. Let me now show you another paper. Okay. But what do you think is the limitation of the paper I just showed you now? If we had to identify a couple of limitations of the paper, what would those be?
So they do it only for 2 and 3 fish. So you don't know if like they behave the same when there are like
15 fish. Yeah, exactly. Very good. Okay. Yeah. That's one very important limitation. Okay, fine. You can think of more. We'll now. I'll show you now one more paper. This is on starling flocks. I already have shown you one paper on starling flocks about how they sort of have these long correlations. So this is another starling flock paper where they basically claim that interaction ruling animal collective behavior depends on topological rather than metric distance. Does that make sense? What is this? Okay, so if you remember Vichek model or cousin model, the basic idea of those models was that fish interact at a distance from one another. Fish or any organism will interact and do an averaging between distance, let's say whatever, 1 body length to 5 body lengths. We'll do an averaging in this well-defined distance units. This is called a metric distance, because it's defined by a regular way we measure the metric distances. Okay. On the other hand, what they're basically showing here is that it doesn't matter. The distance actually doesn't matter when actually starting flocks are interacting. What really matters is the topological. Who is the first, second, third, and so on? Who are the you have to order them by the number nearest neighbors, but not necessarily by the absolute distances. That's what this paper claims. Okay, let's see the abstract. Numerical models indicate that collective animal behavior may emerge from simple local rules of interaction among individuals. However, very little is known about the nature of such interactions, so models and theories mostly rely on a prioristic assumption. By constructing the 3-dimensional positions of birds in airborne flocks with a few thousand members, this is not 1 or 2 members, thousands of members, we show that the interaction does not depend on the metric distance as current models and theories assume, but rather on topological distance. In fact, we discovered that each bird interact with a fixed number of neighbors, 6 to 7, rather than with all neighbors within a fixed metric distance. We argue that a topological interaction is indispensable to maintain flocks cohesion against large density changes caused by external perturbations, typically predation. We support this hypothesis by numerical simulations. showing that a topological interaction grants significantly higher cohesion of aggregation compared to a standard metric one. Is it clear to you? Basic point is this. We showed interaction does not depend on fixed distance, rather than on topological distance. And in case of Starling flocks, we just seem to care about 6 to 7 nearest neighbors, and the actual distance doesn't really matter. And I think basically they sort of show that in this graph. Okay, I think this graph is a bit hard. They measure something called a anisotropy, measure of anisotropy. Okay, and basically, you have to read this paper. There are people who sort of really question the conclusions drawn from this. They basically claim that this anisotropy factor, if you measure it, and they basically claim that wherever this hits 0 is the value after which the fish, not the fish, any organism will stop interacting. Okay, and they find that they hit 0 around whatever, 6 to 7, let's say 6 or so, and if it was a metric distance, okay, this curve, I don't really know how they actually argue why they say that a metric model will not show this kind of a behavior. I have forgotten the details, but the basic idea is based on this measurement of macroscopic quantity. Okay, that they basically argue that the assumptions about the local rules is best fit only if you assume a metric interaction, but not the topological interaction, but not the metric interaction. Okay. But unlike the previous work, here is the important thing. Here they're actually not measuring local level properties. They're actually still measuring what I call Q, a macroscopic quantity. They measure macroscopic quantity, but they are making inferences about the local interaction rules. In that sense, this is not directly a measurement of the assumptions directly, but more indirectly. Okay. But there are other papers like the one that I showed, where they do experiments with just a small number of fish, and they make some similar inferences about how local level interactions happen. So any questions on this? I encourage you to read these papers if you're interested in this area of research. Or broadly thinking about spatial models and how do you make connections between models and data. I think these two studies could be a good starting point. Sort of think broadly. How do you make connection between data and data? Any questions? Okay, so I will stop here. Okay, so we'll meet on next Monday because I think Friday is holiday. Okay. We need to finalize the date for the final presentations and the submission of reports. Okay, I will send an email on that within 1 or 2 days. Okay, for the date and time that works, we may have to do maybe a poll to find out how are our exams. Okay, thank you everyone. Bye.